Okay, so today is lecture 12, neural networks and more. So just to get started, let's first review what we have covered, like the logistic regression classifier. So the last, actually on Tuesday, we covered logistic regression. It's for binary classification. And its most important is this representation of the logit of the log ratio of the target py given x. It's modeled as a linear function of x. And then that derived this the sigmoid plus a summation function that gives us this prediction of how the positive class is going to happen given your x input. So, and then we actually reviewed, so this derives, because this is probabilistic formulation, this actually gives us this loss formulation through the maximal likelihood estimator. And we can derive and then rewrite it. This form is very similar to the entropy type of representation. So actually that's why people call it cross entropy. So essentially that's just negative log likelihood. And then we also provide you a very quick survey about stochastic gradient descent. So that was a really important topic. So during the logistic regression classifier session, we provided you 5 different views. What is logistic? How do we think about logistic regression? So we can first view logistic regression as the logit, like y as a linear x. And then the second view is we are essentially model the y parameter, the output parameter, y variable as a Bernoulli distribution, the binary random variable. And this binary random variable's parameter p hat is a function, is actually parameterized by the x input. The third view we can think about logistic regression is, so logistic regression is kind of a S-shaped compression function on top of a linear regression. And this view actually is very important to introduce the deep learning. And the fourth view we try to introduce is logistic regression essentially models a linear classification boundary. And the fifth view is exactly the next few pages. So we can treat logistic regression as a summation first and then sigmoid next. So essentially the view 2 and view 5, they're actually view 3 and view 5, they're kind of more like the same angle. Yeah, view 3 and view 5. All right, so now let's move to this really popular. So what we're going to cover today is just basic neural network models. So let's, again, using this nutshell view to look at the basic neural network models. So the more general type of thinking, the deep neural networks can model a tabular data. It can also model 2-dimensional, 1-dimensional, 3-dimensional, and graph, or the composition of this different kind of data modality. Deep learning is extremely powerful and flexible platform, and we can think about that. So today I will still focus on tabular data, and the next class will be 2-dimensional data. And it can perform classification regression, the basic case. But actually, in fact, it's also enabled a lot of tasks that doesn't fall into this prediction formulation, like not just classify as some discrete output variable, not just predict some numerical variable. It can generate really complicated images. It can generate really complex and very real text pieces. It can even generate programs, codes. So I will try to cover that in next Thursday's class. So it's just an extremely powerful family of the models. So what we're going to cover today is very basic. We will only touch the multi-layer type of network of topology. And then again, just the cross entropy based loss function for the prediction tasks, what we're going to cover. And we will cover a little bit more about the specialized version in the neural network family. So it's still stochastic gradient descent, but it's more specialized because of layer-wise structure. People call them back probe type of gradient descent-based method. And if time permits, I will also talk a little bit about for the prediction, like classification task. I mean, how do we measure success? So especially on the image type of inputs. All right. So first, so like roadmap today, I will focus on single neuron, this concept of single neuron, and then multi-layer perceptron, then loss function, and then training by back probe. So we actually touched this last time. We can rewrite logistic regression as two-stage representation. So the first stage is Z. We can just use a random variable Z to represent that summation part. And then the second stage is e to the z, e power exponential z over 1 plus ez. And this is a logistic. It's also sigmoid. We call that sigmoid squashing or compression step. And then we show you this like a block or a circle views. And essentially, so this is our z variable, and this in the logistic regression case, the y hat is our prediction. That's just the p hat. All right. Okay, so in fact, we have many choices to replace this compression or that squashing step. So logistic or the sigmoid is only just one of it. And there are many different kinds. You can do a binary step. You can also have 10H. You can also have a rectifier layer. They have all this kind of pretty simple equation, but they all have this more like in the end it's a S or revised S shape. Or this one rectifier layer is a little bit different. It's a piecewise linear squash. And actually now rectifier layer is used more. It's almost the most popular nonlinear layers. Okay, so just a little bit of history. So what we are going to talk about is a multi-layer perceptron. And so why that's called perceptron, right? So there's a history is, so this one neuron unit with the step function is what people proposed as a perceptron. That was proposed in 1950s, and then it's this squash function essentially just you can think of it as a binary decision step. So if the z input is larger than 0, I'm going to output 1. If the z input is negative, I'm going to output -1. It's like a binary classification, this smaller node. And this type is in the history called perceptron, but now people just generalize. So I mean, kind of relax this stepping function to many different kinds, and there are actually many. So this page gives you, again, on the left, we know the sigmoid, we know the 10H, we know the ReLU, and on the right is something like it's more newer stepping function or compression function, like this leaky ReLU, max out, ERU, and there are S-ReLU. There are many possible such kind of stepping function, squash compression functions. All right, so there are students actually ask about the bias term. So we're always saying that's a pseudo X, right? So do you need that pseudo features? I was not completely clear in the previous class. So in the X, so we can represent all the features as X1, X2, X3, like they're the different nodes. In this case, 3 nodes. You should have a bias term. This bias term is we can represent as a pseudo features, or in many cases in the future, like people actually don't write this, and they directly write the bias term here. So that's a more concise visualization way, because you don't need to write like an extra node plus this arrow, right? So, but you need it. So the reason why we need that bias term, so it's very clearly described by this figure. So if we don't have bias term, we don't learn the bias parameters. So think about, so this is multiple whatever x, so this is one dimensional. So this x-axis is just one dimensional x, and this output is, I think this, let's think about this is the sigmoid z. Z, it's some kind of x, z equals to alpha x, so in this case. And which makes what? I mean, everything here, no matter what is the alpha you learn, 1x equal to 0, and that sigmoid z always is this point, 0.5, right? So which means what? I mean, if your x is 0, no matter what you learn, you're always going to give a 0.5 from this type of learning like blocks. Which is actually bad if you think about it. So if you allow the bias term, you're giving many possibilities, and then to have a lot of flexibility. You can model almost just from left to right all the possible cases of this S shape. Yeah, so that's one point I want to emphasize. Yes, bias term should be learned, and it's important. Okay, so now it's multi-layer perceptron. So what is multi-layer perceptron? Essentially, it's very simple. So we can think about this summation layer and this squashing layer together as one unit. And this one unit, we just treat this as one neuron. So from here, I'm not going to draw that bias term, but you should remember there's a bias term. And you can just represent the bias term actually inside this sigma here. So, or as part of this, there's a B here, and you need to learn it. So the linear transformation and nonlinear together, we consider this as a single neuron. And then we can just replicate. And we can have many neurons in one layer. We can also stack the neurons after my neuron outputs. So the neuron in this same, if you do this, just concatenate their input is from the same kind of layers, and there are multiple outputs. This is this treated as multiple neurons in the same hidden layers. And in this case, I have 4 neurons in my first hidden layers. Then after first hidden layer, I have another hidden layer. It's my second hidden layer. I also have 3, but it's not necessary. I also have 4, but it's not necessary to be 4. I can have 3. I can have 5. It's really the designer's choice. And then because now I'm trying to show you a binary classification. So for the binary classification, the last layer essentially is this single neuron. It's a single neuron with a summation plus a sigmoid, because we want to present p hat, right? P y equals to 1, condition on x. So this essentially gives us this y hat. I mean, that sigmoid, last sigmoid layer, give me that. All right, so this is for all the binary classification, your last layer needs to be that one neuron with sigmoid as the compression function, nonlinear components. Okay, so and then you can actually write out how from the x onto the y, and then there are a lot of middle layers. You can just represent them in this case. So this has z1, and then got compressed into h1, and from h1 and the summation of w2 go to z2, and then from z2 go to h2, right? So it's really this kind of feed forward signal. If you think about the signal is x to z1 and parameterized by the W1, and z1 goes to h1. There's no parameter because that's just sigmoid layer. From h1 go to there's W2 go to Z2, then Z2 goes to H2, H2 there's a W3 and plus then another sigma, there's no parameter, then goes to Y hat. All right, so this is pretty, like, this is really you feed the X and then loop and just forward, calculating the Z1 and just step by step calculating all those relevant variables by using the parameters of that specific layer. So very simple and very straightforward. Okay, remember that. In fact, this is exactly the forward step in the later we're going to learn the back probe. This is forward step. Remember this. You have the X, you feed in this layer by layer by calculating all those middle level variables, and you memorize them too. Okay. All right, so that's the one we just showed you has only 2 hidden layers and 1 sigmoid this output layer for binary classification. That's the very, very simple multi-layer perceptron model. But state-of-the-art actually has much more complex type of neural network models, which we're going to cover in details. That is the convolution neural network model. It's the homework 3 you're going to use. Almost the most popular, the deep learning type of neural network models, it's this convolution neural network model, CNN, and there are many different kinds. And so you can actually see, so this is really, it's actually already old. So in the 2010, that ImageNet competition we reviewed in the first few class, and they are pretty shallow. And then 2012, and this is like 8 layers, that's AlexNet. And then in 2013, like 8 layers. And then in 2014, Google has this 152, but actually now it's even deeper. I think it's a little, yes, I believe there are deeper models. And VGG model is a very popular model people normally use. It's like 19 layers, and the one I just showed you last time, the ResNet, I think 34 is the one I show you. They're actually even bigger ones. Yeah. All right. So just give you a rough idea the number of layers in the state-of-art models, and what we're going to show you is actually much simpler. Normally just 2 layers. Okay, so now I want to review the fourth view we actually told you about logistic regression. So we actually proved the logistic regression, the decision boundary is a linear line. So this is very important in the 2-dimensional case. In the high-dimensional case, it's a hyperplane. So it's very easy to prove. Decision boundaries are those points you cannot make a decision. In this case is p equals to 1 and py equal to x and py equal to 0. Let me change to blue color. They equal to each other, so which means they each is 0.5 because they're binary discrete variables, right? There's only 2 outcomes. Yes and no, 1 or 0. So only the points with 0.5 probability, you cannot make a decision. All right, so keep that in mind. And the points in the 2-dimensional case, the decision boundaries are decision lines. So what I want to show you now is if I have this one, it's a 3-layer, actually 1-layer neural, like MLP. So I have this neuron, maybe let me just call it H1, H2. Oh, this uses X and Y. I don't like that. So I want to change this X1 and X2. Yeah, so let's keep that. So I have a 2-dimensional feature, X1 node, X2 node, and I feed into a hidden layer with only H1 and H2. I need to feed into both, right? Because this is So think about that forward. I'm feeding it into there. So that's why there's an arrow there. And H1 give me, it's a neuron. There's a sigmoid there, remember? And H2 output. And H1, H2, and then together goes to, let me just see, that's Z, or maybe Y. This is my classification. They're all in 2 classes. And all these layers, except the input layer, they are the sigmoid version of the neuron. All right, so what I want to show you is the geometric view of the decision boundary for such a simple MLP. So we actually know, right? Each neuron essentially is a sigmoid. It's a logistic regression. And what logistic regression gives me is a linear decision boundary. In the 2-dimensional case, it just segments the input space into two parts. So this is the first. So this is the H1, and this is the H2. And when I'm putting them together, so this is the most important I want to deliver in this page. So what is when you put 2 neurons, 2 linear decision boundary together, what do you make? So this figure actually shows you very nicely. So when you have H1 is a linear decision boundary, H2 also give a linear decision boundary together, they are creating this nicer non-linear decision boundaries. And you actually can, I think my next page trying to show you, you can use the weights actually to understand. So let's understand this. So this is essentially the weights, right? So go to the H1. So again, this is X1 and X2. And here is X1, X2. The color here means the Y. Okay. So X2, X1. So you can actually think about the weights, right? So the first give me plus minus decision boundary. The second neuron, so H1 and H2, H1 and H2. So it's actually pretty tricky why in this region, right? Let me actually copy this here. So think about this, vote this part as positive, and this one vote this part as negative. How come the final decision make that part as a positive? I mean, there's no doubt of those shared place they share. So think about this region is minus, right? That's very clear. It's the minus. And this region is the positive. They both predict that as a positive. So it's the interesting part, the area they don't agree. And that's how your weights combine the two, actually have influence, and also that bias term. Actually together, it's a composition of 2 decision lines to make a non-linear decision lines. I hope this gives you a little intuition how the simple 2-layer network worked and to generate a non-linear decision lines. Okay, so the other thing I really want to emphasize is, so let's come back to think about this squashing or compression view. So this is a 1-dimensional, right? So this is my Z. So assuming this is my Z, and this is the sigmoid Z, right? So this is the sigmoid Z. Sorry. So let's actually see. I mean, if you look at the range here, 1Z is smaller than -5, and that sigmoid Z is just completely 0, right? It gives me 0. And when this Z is larger than 5, I mean, it's a plateau, right? So it's like, so this reaches a plateau, this reaches plateau, and this almost gives me the output as 1. So which means what? Let's look at this figure. So if assuming your that Z variable is uniformly, data is uniformly distributed in this minus infinity to positive infinity. And actually the squashing function really compress everything into 0, 1, and compress more in the two sides, in the two ends. It compress less in this middle part. And then this kind of nicely reflected if your input, so the left part is the z, so the left part shows me the z, and the right part shows me the sigmoid z. And it doesn't distribute uniformly anymore, so keep that in mind. And so for those are actually like those very close to the decision boundaries, and they're pretty, the probability actually changes a lot in the decision close to decision boundaries. One is just a little bit far away from the decision boundaries, then everything got the same result. So this, in fact, got reflected in this figure. You can see a little bit clearer. I think maybe this figure is clear. Then let me summarize. I talk about simple multilayer network topologies, and I also talk about geometric views of a very simple one hidden layer MLP. And also I introduced this feed-forward concept from the x to the end y. And there are many middle variables you need to calculate. And this is the first module. All right. So